Hi guys, this is Dr. J here, and in this video we will talk about chair conformation of cyclohexane, and especially when you have substituents present on cyclohexane, how their conformations change and the stability of different conformations. So if you take a look at the chair conformation for two conformations of methyl cyclohexane. Okay, so you can draw two conformations for methyl cyclohexane. As you can see, these two are different. Why? Because in one conformation the methyl group is in an axial position, and the other conformation the methyl group is in an equatorial position, right? So because of that, these two conformations are different from one another, but these two conformations are not equal when it comes to stability. Okay, one conformation is actually more stable as compared to the other conformation. In fact, the conformation where you have the methyl group in equatorial position, okay, so when you have the methyl group in the equatorial position, this is more stable as compared to the other. So in this video, we will try to understand how these stabilities are changing, what type of energies we have to consider when we are talking about these stabilities, and we will also talk about di and tri-substituted cyclohexanes and their chair conformation stabilities. So when we talk about the concept called ring flip, I mentioned in that lesson, when a ring flip happens, you always exchange the equatorial groups to axial groups, right? So in here, even though the CH3 in the axial position and equatorial position, they are two different conformations. After a ring flip, these equatorials can easily become axial, and axial becomes equatorial, right? So because of this equilibrium for the ring flip between the CH3 group in axial position and the equatorial position, ideally you expect them to be present 50-50, but since when you have the CH3 group in the equatorial position, when you have equatorial substituents, they are more stable, and therefore equilibrium tend to shift towards the right hand side in this example. So energetically speaking, okay, it is more favorable to have the more stable conformation. So with time, all the axial conformations will convert to equatorial conformations. Why? Because it is more stable. So in the beginning, okay, you will have 50-50 axial conformation and equatorial conformation, but with time, equilibrium will shift to the more stable isomer, in this case the equatorial isomer, and therefore you will have almost 100% of the more stable conformation as compared to the unstable conformation. Okay, so that is how the equilibrium shift depending on the stability. And in fact, the other important thing to remember is that this equatorial conformation, when methyl group is in the equatorial position, this conformation is actually 7.6 kilojoules per mole more stable. Okay, this is kilojoules 7.6 per mole more stable as compared to the axial conformation. So that is why equilibrium will easily shift into the more stable equatorial conformation. So now let's try to understand why these equatorial substituents or conformations are more stable as compared to conformations where you have axial substituents. Okay, so what happens is that whenever you have axial substituents, they can cause steric strain. Okay, they can cause steric strain with other hydrogens or substituents. Okay, so if you consider a methyl group, that is present in the number 1 carbon, okay, if you consider a methyl group that is on the number 1 carbon, of course this is in the axial position. Why? Because it is pointing up, right? It is pointing up, and this carbon is also pointing up. So this is an axial carbon, and the methyl group is axial. So if you have an axial methyl group on the number 1 carbon, it can display steric interactions with axial hydrogens. It can display steric interactions with the axial hydrogens from carbon number 5 and carbon number 3. Okay, carbon number 5 and carbon number 3. So each of these steric interactions are worth 3.8 kilojoules per mole. Each of these interactions worth 3.8 kilojoules per mole. So you have two of them. And therefore the overall instability for this conformation will be 7.6 kilojoules per mole. Okay, so you have two steric interferences or interactions between the axial substituents, and the carbon number 5 and carbon number 3 hydrogens which are also axial. Okay, so because of these axial interactions, you have 7.6 kilojoules per mole worth steric interactions. And in chemistry, we have a name for these steric interactions, these axial steric interactions. We call them 1,3 diaxial interactions. 1,3 diaxial interactions. So for methyl groups, each 1,3 diaxial interaction is 3.8 kilojoules per mole of steric strain. And when this ring flip happens, all the axials will become equatorial. So the methyl group will go from the axial position. It will go from the axial position to an equatorial position. And when the methyl group moves to an equatorial position, you no longer have these aligned 1,3 diaxial interactions. Okay, you no longer have these steric interactions. So therefore, when the substituent or the methyl group in equatorial position, it is 7.6 kilojoules per mole more stable, because there are no 1,3 diaxial interactions. That is why the equatorial position, the conformation that contains an equatorial substituent, is more favored. Okay, this is more favored. Okay, more favored. That is why the equilibrium shift to right. Maybe you might be a little bit familiar with this 3.8 kilojoules per mole. Okay, you might be familiar with this specific amount of energy. We talked about it when we talk about alkane conformations. We talked about gauche conformation, right? In gauche conformation, what happens is that you have two CH3 groups 60 degrees apart. It is a staggered conformation. And in this gauche conformation, you have two methyl groups 60 degrees apart. So you can actually explain these 1,3 diaxial interactions using gauche conformation. Honestly, it is basically the same thing. Okay, why? Because you can draw the cyclohexane ring using Newman projections, and of course you have let's say this is your carbon number 1, then this is carbon number 2, carbon number 3, carbon number 4, carbon number 5, and carbon number 6. Okay, so as you can see, this CH3 group basically is similar to the CH3 group right here in the gauche butane. Okay, and then you also have another second CH3 group right here, which is causing the gauche interaction, and then that CH3 group is actually a CH2 here. I mean, this is a CH2 group which is basically identical to the CH3 group interactions. Okay, so this CH3 and this hydrogen on the number 3 carbon will have gauche interactions. Okay, gauche interactions which is worth 3.8 kilojoules per mole. So the gauche interaction between this hydrogen and the CH3 group is 3.8 kilojoules per mole. So if you don't remember gauche interactions, I would recommend you to go back and revisit it. Okay, revisit the conformations of alkane lecture video. Okay, but basically this 1,3-diaxial is what? 2 gauche interactions. So you can similarly, I mean, visualize this CH3 having another gauche interaction with this hydrogen, which is another 3.8 kilojoules per mole. So overall, when you have a cyclohexane ring, axial methyl groups will have 2 gauche interactions with carbon number 5 and carbon number 3, which is basically giving you 7.6 kilojoules per mole of steric strain. Of course, when you have different substituents, these energy, the energy of 1,3-diaxial strain will be different. Okay, so we already learned about methyl group, okay, which is 3.8. But of course, I mean, this is the energy for only one interaction. So you always have 2, right? You always have 2. So that is how you get 7.6. But as you can see, if you have bigger substituents, then the steric strain is even larger. Okay, see, if you have bigger substituents, the steric strain is even larger. But I'm not going to ask you to memorize this. Okay, I'm not going to ask you to memorize this table. No one has to do that. Okay, but honestly speaking, this is what you need to understand. The bigger the substituent, okay, the 1,3-diaxial interactions are going to be high. Okay, so when you have, so the take home message is, whenever you have a very big substituent, you should try to put it in an equatorial position. Whenever you have a big substituent, always try to put it in an equatorial position, so that you will not have these 1,3-diaxial interactions. Okay, keep that in mind. So next, I want to see if you could try this example problem by yourself. Okay, so you might want to pause the video and see if you could do this without my help, and in a second I will explain you how to do it. Alright, so using the data from the previous table, I want you to see if you could calculate the energy difference between axial and equatorial conformations of cyclohexanol. Okay, cyclohexanol. So let's see. First of all, draw 2 chair conformations. Don't think about the question, okay? Don't get confused. First, draw 2 chair conformations. This is the first thing that you will do. See, don't think anything. Just draw 2 chair conformations, and then you want to put an OH group, right? So in first chair conformation, I'm going to put the OH group in the axial position, and the other conformation, I'm going to put the OH group in the equatorial position. Okay, so when you have an OH group in the axial position, it is going to have 1,3-diaxial interactions between the other 2 hydrogens, other 2 axial hydrogens that are pointing upward. Okay, so you're going to have 2 1,3-diaxial interactions. So each interaction is how much? If you take a look at that table, each interaction is 2.1 kilojoules per mole. So you have 2 of them. So the total energy will be 4.2 kilojoules per mole. So the total energy will be 4.2 kilojoules per mole. So therefore, the conformation with OH group in the equatorial position, this one is more stable. By how much? By 4.2 kilojoules per mole. Okay, that is how you understand and answer these type of questions. Alright, so now we are going to move into the most complicated part of the lesson, which is disubstituted cyclohexanes. Okay, so when you have two substituents on cyclohexane, you have to consider steric effect of both substituents. Okay, both substituents. So there are three type of cyclohexanes could be possible. Okay, so let's try out these three types of cyclohexanes. Okay, so you can have the two substituents on the 1 and 2 carbon. Okay, you can have the two substituents on the 1 and 2 carbon. Okay, so you can have the two substituents on the 1 and 2 carbon. Let's say this is X and Y. Okay, or you can have the two substituents on the 1 and 3 carbon, right? Or you can have the two substituents on the 1 and 3 carbon. So X will be on 1 and Y could be on 3. Or the last example is where you have the two substituents on number 1 and number 4 carbon. Number 1 and number 4 carbon. So X will be right here and Y will be right here. Okay, so these are the three possibilities. These are the three possibilities that you can have. Alright, so these are the three possibilities that you could have when it comes to disubstituted cyclohexanes. The two substituents could be on 1 and 2 carbon, or the two substituents could be on 1 and 3 carbon, or the two substituents could be on 1 and 4 carbon. So as an example, I am going to take 1,2-dimethyl cyclohexane. Okay, so when it comes to 1,2-dimethyl cyclohexane, so you have two methyl groups on the number 1 and number 2 position, and you could have a cis isomer or you could have a trans isomer. So let's figure out which one is more stable. Okay, this part of the video is extremely important, so pay attention. All right, so we are trying to figure out which conformation or which isomer is more stable. Is it the cis isomer or is it the trans isomer? So let's talk about the cis isomer, which means both CH3 groups are on the same side of the plane, right? So let's try drawing the board conformation for it. So now you don't have to draw all the board conformations. Okay, you know you only need the most stable board conformation. How do you get the most stable board conformation? You are looking for the most stable one. So if you want the most stable conformation, you should look for equatorial substituents, right? You should look for the equatorial substituents. So right off the bat, pick a carbon. Okay, so let's say you want to pick these two carbons. This will be your number 1 and number 2 carbon, right? So when you start with the first carbon, always start with an equatorial bond. Always start with an equatorial bond. So I'm going to put my CH3 on the equatorial. And is it pointing up or is it pointing down? Is it pointing up or is it pointing down? It is pointing down, right? So since this is cis, the other CH3 group should also be pointing down. Okay, so this is what I get. Okay, so both substituents are pointing down. So this one is cis. But let's look at the equatorial ones. Okay, let's mark them in teal. Okay, so this one is equatorial and red one is axial. Okay, so this one is axial, which is not good. Blue one is equatorial. This is good. So when you have a CH3 group on the axial position, you have 7.6 kilojoules per mole energy. Okay, so for the cis conformation, this is the most stable one. So let's try the trans conformation. So here's the trans conformation. We need to draw the chair conformation for trans, and then first of all draw a chair conformation, and we only need the most stable one. I know in the textbooks they are drawing like 2-3 chair conformation, then figure out which one is more stable. You don't have to do all that. Okay, draw the most stable one. How do you draw the most stable one? You will draw a chair conformation, pick the two carbons of interest. These are the two carbons of interest, and then when you start with the first carbon, put the bond in an equatorial position. So this will be equatorial. So this CH3 is in equatorial. That much is understood. Okay, this CH3 is in equatorial position. And this is a trans molecule. So here's the other carbon. And in trans molecule, the two CH3 groups should be on two opposite planes. This CH3 group is on the bottom plane. This is on the bottom plane. So the other CH3 group should be on the top plane, right? The other CH3 group should be on the top plane, and it is also equatorial. Okay, so one CH3 group is on the bottom plane and the other CH3 group is on the top plane. So this is trans, not even that it is trans, this is also equatorial. So as you can see, when you compare the cis and trans chair conformations, you can clearly see that cis is not stable as compared to trans. Why? Because cis has 7.6 kilojoules per mole of steric strain as compared to trans. Therefore, trans conformation is more, trans isomer is more stable. So when it comes to cis and trans isomers, so 1,2 disubstituted cyclohexanes, trans is the most stable one. Okay, trans is the most stable one. Keep that in mind. So we already learned 1,2 dimethyl cyclohexane as an example for 1,2 disubstituted cyclohexanes. So let's talk about 1,3 dimethyl cyclohexane. I mean, if your light bulb hasn't gone up yet, I mean, this part of the video should help you to understand how to figure out which isomer is more stable as compared to the other. Okay, so when you have a 1,3 disubstituted cyclohexane, which isomer is more stable? Is it cis or is it trans? Let's figure it out. So for this, you're going to have to take one isomer at a time. So let's talk about cis isomer first. For cis isomer, you can draw two conformations, two chair conformations. Okay, so quickly draw two chair conformations. So but you don't have to do both of them. You only have to draw the most stable one. So if you want to draw the most stable one, you will first figure out the two carbons of interest. So this is carbon number 1 and carbon number 3. You will figure out that, and then for the first carbon, put the substituent, put the methyl group on equatorial position. Okay, so CH3 group will be on the equatorial position. Why? Because equatorial position is the most stable position as compared to axial with no 1,3 diaxial interactions. So first CH3 group will go there, and then it is at the bottom plane because it is going down. As you can see, it is at the bottom plane. So this is cis. We want to make sure that the third carbon also has a CH3 group that is going down, right? That is going down. So the good thing is, if you draw the CH3 group going down, you realize that that is also equatorial, which is more stable. So in cis 1,3 dimethyl cyclohexane, there is no steric strain from 1,3 diaxial interactions. So therefore this is stable. This is stable as compared to trans. But if you don't believe me, let's work it out. Okay, let's work it out. So similar to the cis isomer, you can draw the most stable chair conformation for trans. Okay, so here are the two carbons of interest. Okay, and always start the first carbon with a equatorial substituent, because we are looking for the most stable one. You can draw two chair conformations for trans, but don't waste your time. Draw the most stable one. So the first isomer will be on the equatorial position, and then it is at the bottom plane. Okay, it is at the bottom plane. Okay, so since this is trans, the next substituent should be on the top plane. Next substituent should be on the top plane, which means this carbon will have the CH3 group on an equatorial position, which we don't want, but it is what it is, right? So this CH3 is on the top plane and it is an axial one. Okay, it is on the top plane, but it is axial. So when you have a axial CH3, of course you are going to have 7.6 kilojoules per mole steric strain. Okay, so you're going to have 7.6 kilojoules per mole steric strain. So this is the unstable one as compared to cis isomer. Okay, so here's the cis and trans together. As you can see, for the cis isomer, you have the most stable conformation. Why? Because there is no 1,3 diaxial interactions. But for the trans isomer, the most stable, even the most stable chair conformation has one CH3 group in the axial position, so therefore it is unstable. So out of the two isomers of 1,3 dimethyl cyclohexane, out of the two isomers of 1,3 dimethyl cyclohexane, of course cis isomer is more stable. I mean, you can do the same for 1,4 disubstituted cyclohexanes, and then you will figure out that that is the trans isomer is the most stable. Trans isomer is the most stable for 1,4 disubstituted cyclohexanes. Okay, I mean, you can try to work it out, but here is the summary of what we learned. Okay, so if you have a 1,2 disubstituted, cyclohexane, of course the trans isomer is the most stable one. Okay, trans isomer is the most stable one. Okay, we worked it out. If you have a 1,3 disubstituted cyclohexane, cis isomer is the most stable one. Okay, so if you have a 1,4 disubstituted cyclohexane, trans isomer is the most stable one. Okay, why? Because both substituents will be on equatorial position in these chair conformations. So if you didn't understand anything, just remember this. I mean, if you have a 1,2 disubstituted compound, a trans isomer is more stable. If you have a 1,3 disubstituted compound, cis isomer is more stable. And if you have a 1,4 disubstituted compound, then trans isomer is more stable. If you remember that, I mean, you can still get the correct answers most of the times, but it is not the preferred method. Of course, you should try to understand it, but worst case scenario, you can try to remember the highlighted parts. So let me draw these, okay, so that it will go into your head better. Okay, so if you have the two substituents on 1 and 2 positions, this is trans. If you have the two substituents on 1 and 3, then this is the most stable isomer, which is cis. And if you have a 1 and 4, okay, if you have 1 and 4, then this will be the most stable isomer, which is a trans. Alright guys, with that our lesson is complete. So let me know if you have any questions. Okay, you guys have a good one. Take care.